calculations in Chapter 6. Chapter 6 has many formulas in it, and being able to use those formulas and know when to apply them is a skill that you'll have to develop. So to start with, we've got a couple on the screen here where you've got the speed of light, c, call that's 3.00 times 10 to the 8th meters per second. You'll see other values for that, but we'll go by the value that's given to you on your things to memorize or the periodic table you'll be given on your exams. But the speed of light in a vacuum is equal to the wavelength of the light times its frequency, so lambda nu. This formula here, the energy of a photon is equal to h, or Planck's constant, times the frequency nu. Also, from these two equations, you have E, the energy of a photon, doing a little algebra, is equal to hc over lambda. So that's just combining these two equations. So energy of a single photon. But given these three equations, you can calculate three entities. You can calculate the energy of a photon, or energy relations, or energy, the frequency of light, and the wavelength of light. So the symbol for frequency is nu, Greek letter nu. The symbol for wavelength is lambda, light, or lambda wavelength. When copper is bombarded with high-energy electrons, X-rays are emitted. Calculate the energy in joules associated with the photons if the wavelength of the X-rays is 0.154 nanometers. Okay, so previously there are three equations. Two of them you've got to commit to memory. The third one you can derive if you're savvy with algebra, that relate energy, wavelength, and frequency. So it's good to write those equations down. E is equal to h nu, and the speed of light is lambda nu. The question is asking for energy of the photon. What's given is wavelength, nanometers. So the formula that's needed is the one when we substitute nu is equal to c over lambda. Nu, this term can be substituted in for here. Energy of the photon can be calculated using the formula just shown. Planck's constant That's the unit for Planck's constant. Make it a little smaller, give myself some room. C is the speed of light. It's important to write down your units because meters, nanometers. Remember, 1 nanometer is 10 to the minus 9 meters. So 0.154 nanometers. Nanometer is 10 to the minus 9 meters. Nanometers cancel. Get 1.54 times 10 to the minus 10 meters. So you got to be mindful of your units. Meters cancel, seconds cancel. You're left in units of joules, and a joule is a unit of energy. Reframing, resizing. If I do that math correctly, I get 1.29 times 10 to the minus 15 joules. That's the energy of a single X-ray photon that has a wavelength of 0.154 nanometers. Energy, wavelength, frequency calculations continued. Ultraviolet light emits a total of 2.5 times 10 to the minus 17 joules at a wavelength of 9.8 times 10 to the minus 7th meters. How many photons does this correspond to? Okay, so for this type of problem, you need the following equation. Where you have a total energy, this value, so a total energy of 2.5 times 10 to the minus 17 joules, and the energy of a photon, which previously, if you're given a wavelength or frequency, you can calculate the energy. So this becomes, we're given the total energy, it's given. We've got to convert this number into an energy. When you're given a wavelength, you use the formula hc over lambda. Lambda is the symbol for wavelength. Planck's constant. Speed of light. Make things a little smaller. Provide some room. Meters per second. The wavelength that we're given is in meters. Times 10 to the minus 7 meters. Units cancel. We're left in units of joules. If I do that math correctly, I get 2.03 times 10 to the minus 19 joules. That's the energy of the photon. So we substitute this value in here. Total energy is 2.5 times 10 to the minus 17 joules. divided by the just calculated energy of the photon. So 10 to the minus 19 is 2 orders of magnitude smaller than 10 to the minus 17. So we should get a large number. Now, not super large, but 123 photons. So this problem makes it a little bit different. Is you have some total energy that's in an emission of light, a burst of light, some larger number, and then you divide that by the individual photons' energies to figure out the number of photons. Another way of doing this problem is using dimensional analysis. So you've got 2.5 times 10 to the minus 17 joules. Get units to cancel. You've got 2.03 times 10 to the minus 19 joules in 1 photon. So joules cancel. And what you're left in is photons, and you get 123 photons.